Hi, all. Let's take a look at section 5.2. It's a pretty straightforward section. We're talking about the definition of a definite integral. And we've already looked at this a little bit in section 5.1, wherever we found area under a curve. And we said, well, we can use left-hand rectangles, midpoint rectangles, and right-hand rectangles in order to estimate that area under a curve. But all three of those techniques, it was just trying to estimate what the integral of a function does. And so now in section 5.2, it formally introduces the concept of an integral. It says that the integral from a to b of f of x with respect to x, and that's the way you would read this, the integral from a to b of f of x with respect to x, and it also means the summation of the height times the width, just like we talked about in the last section. But anyway, the integral from a to b of f of x dx, it represents the signed area between f of x and the x-axis from the interval starting at a, ending at b. So I went ahead and drew a picture here to represent that scenario. We have some arbitrary function f of x. And in this case, I drew the function f of x as an always positive function on the interval ab. And so that area between the curve and the x-axis, a, would be represented between the interval from a to b of f of x dx. Whenever we integrate the function f of x, and we'll talk about our formulas for integration in upcoming sections, but the integral of lowercase f of x is denoted by a capital F. So whenever we integrate this function, you would take whatever the integral is and you would evaluate it at the top limit. That's the integral evaluated at b. And then you always subtract the integral of f as capital F evaluated at the lower limit a. So we'd say, well, it's just whatever the antiderivative where the integral of f is evaluated at b minus the integral evaluated at a. Now, if I wanted to change the sign of that area and say, well, what if I wanted to get a negative area? No big deal. All you'd have to do is just flip your limits of integration. Instead of integrating from a to b, integrate from b to a. And the reason that that's going to give you the negative of the answer, think about what's going to happen over here. Now you'd evaluate your integral at a first, and you would subtract from that the integral evaluated at b, which is the exact opposite sign of the previous case. So you'd say, well, yeah, of course, it's going to give you negative area in that case. Now, what if your function is already, to begin with, beneath the x-axis? So I've drawn in this scenario where my function f of x on the interval from a to b is always beneath the x-axis. If I wanted to find that area a inside of there, I have to understand that the integral of f of x dx, it's not going to give me a positive value for a, it's going to give me a negative. And the reason it's going to give me a negative is because all of my area is beneath the x-axis. So if the area is above the x-axis, you'll get a positive answer. If the area is below the x-axis, you're going to get a negative answer. But now, what if I wanted the true area of that? I don't want a negative. I want to say, well, area can't be negative. I need a positive value for it. Well, all I would need to do is say the true area is going to be the absolute value of this integration problem. And then that's going to be the absolute value of whatever my function is with respect to x. Now, there's no such thing as the integral of an absolute value. So if you automatically know your region is always negative, then one way to integrate the absolute value without putting the absolute value in there, just like I did up here, just flip those limits of integration. Instead of from a to b, if you know you need a positive answer there, integrate starting at b and integrate up to a of f of x dx, and it will guarantee that you get a positive value for your area in there. Now, we'll talk about other ways to deal with absolute values in upcoming sections, but this would be a good way to get rid of this one. Just flip the limits of integration. Now, the integration power rule, and your book doesn't officially introduce it until the next section, but it's helpful in some of the problems here, so I'll go ahead and talk about it. If I have the integral of x to the n with respect to x, and we talked about this in the last section too, it's just the reverse of what you did in Calc 1 with the derivative. You take the derivative of x to the n, you say it's n times x to the n minus 1. You bring the power down in front, and then the power raised to the 1 less power. Exact opposite order now. Instead of decreasing the exponent by 1, you're going to increase the exponent by 1. And then instead of multiplying by that new exponent, you divide by it. So now, in an indefinite integral, you always need to account for there could be some constant of integration. And that's because this has to stand for the original function that you can take the derivative of and get to this function. Well, you know that the derivative of any constant is 0. So working backwards to the antiderivative, we have to say, well, you could add or subtract any constant. And C automatically stands for any number. So you never need to say, does it need to be plus or minus C? Automatically, C is every single positive or negative number in existence. So it'd be silly to say a minus C. Plus C is all you ever need there, the constant of integration. Now, if I worked backwards though, and I said, well, let's take the derivative of this, the n plus 1 would come down, cancel out that n plus 1, then you decrease the power by 1 to get to x to the n. So you can easily, should be able to take the derivative of any answer to get back to what was inside of here. Now, let's look at our first example in this section. And I'm wanting us to integrate from 0 to pi of the cosine of x with respect to x. Now, the goal of this section really is to get you to think about these integrals graphically and stuff. So that's what I want to talk about first in this problem. If I ask you to graph the cosine function from 0 to pi, very easy to graph. We know the cosine of 0 is 1, cosine of pi over 2 is 0, cosine of pi goes to -1. So the cosine function between 0 and pi looks something like this right here. Now, what the integral from 0 to pi is going to do is it's literally going to block off your function from there to there and say, hey, what's the area from here to here? Well, whatever the area is here, it's going to be equal and opposite in this region. So I can say, well, that's just going to cancel each other out, and those areas would give me a sum of 0. Now, to see that play out as far as how we actually take the integral, again, you need to think of it as the reverse of Calc 1. So it's like playing Jeopardy with all of your problems. In Calc 1, you'd have to say, well, what can I take the derivative of and get a cosine? Sorry, what can I take the derivative of and get a cosine? You can say, well, the derivative of sine is cosine. So the integral of cosine is sine. Now, a lot of people, you're used to taking the derivative. So often see students make the mistake and they'll say, ooh, negative sine here, because the derivative of cosine is negative sine. What you can always do when you take the integral of sines and cosine is take the derivative and then always change the sign. It's always the opposite sign. So derivative of cosine would be negative sine. Well, integral of cosine is positive sine. And again, it's because you can take the derivative of this to get to this. Now, after I integrate, I need to evaluate at the limits of integration from 0 to pi. Well, sine evaluated at the top limit gives me sine of pi minus sine evaluated at the lower limit, 0. But whether you're taking the sine of pi or the sine of 0, both of those answers are 0. So we just have 0 minus 0 is 0, which matches our answer that we did graphically, which is cool. Up next, if I look at another problem here with you, let's look at the integral from -5 to -1 of 8 with respect to x. Now, first of all, if I just did this with my integral power rule, I would understand that the inside is understood to be 8x to the 0. So if I increase the power on that x, it becomes 8x to the first divided by 1. You don't need to put a 1 in the denominator. Now, you would take that integral and evaluate it at the limits of integration, which gives me 8 times -1, and you always subtract the lower limit, minus 8 times -5. This would give me -8 plus 40. Well, 40 minus 8 gives me a 32. Now, again, the goal of this section really is to get you to think about these graphically. And you say, well, the graphical analysis, what is -5 to -1 of 8 dx trying to do? Well, it's trying to get you to think about how much area is under the curve y equals 8 from -5 to -1. And you can say, well, it's just a rectangle that has a base of 4 and a height of 8. So the area would be 4 times 8, 32. Our answers match. Of course, they should. Now, similar to this last one, what if I ask a question like this? How large could the integral from 0 to 6 of f of x dx be if I told you that f of x always had to be less than or equal to 1/3? Well, we know that the integral is just the area under the curve. So if the curve f of x is at most 1/3, then you could say then the absolute most area you could ever get is when f of x is the largest it can ever be of 1/3, and the integral would be the area from 0 to 6. And so you'd say, well, it'd be the area of a rectangle with a base of 6 and a height of 1/3, which that area is 2. Now, that would be the most this integral could ever be if f of x is at most 1/3. If f of x is less than 1/3, of course, your area under the curve would be less than that. That would be the maximum area. Pretty cool problem. Now, we get to a problem with an absolute value in there. And recall what I said at the beginning of this section. There's no such thing as the integral of an absolute value. So you cannot leave an absolute value inside of your problem. So for number 4 here, I'm wanting you to consider the integral from -1 to 1 of 2x minus the absolute value of x with respect to x. So before I do that, I'm thinking every single absolute value function is a piecewise defined function. So I know that the absolute value doesn't have to do a thing. The absolute value of x, it's just x if x is already 0 or a positive number. The absolute value does nothing. But the absolute value is going to change the sign on x. The absolute value of x is going to equal -x if x is a negative number. So then I'm going to have to break apart this integral from -1 to 1, which would represent the area from -1 to 1 under this. I can't think about it all together with that absolute value in there. So I can say, well, let's break it apart and say from -1 to 0, in this entire region, the x values would be negative. So I'll say, well, then this is going to be the integral of 2x minus, replace that absolute value of x with a -x, because you know anytime x is negative, the absolute value of x is going to make it positive. So you say, okay, that's going to take care of that. Plus, the rest of the integral would start at 0 and go up to 1. And please keep in mind, there's no option. This problem had to be broken up into these two components. In this region, x is negative, so the absolute value of x is -x. In this region, x is positive, so the absolute value does nothing. And you'd say, it's instead of 2x minus the absolute value of x, it's just going to be 2x minus x. Now, I simplify each of those, of course. The first one's going to simplify to be 3x, the second one just x. And so now I integrate. The integral of 3x becomes 3x squared over 2, or 3 over 2x squared. You're evaluating that from -1 to 0. Your second one becomes x squared over 2, and you're evaluating that from 0 to 1. Now, when we evaluate this first one from -1 to 0, the first thing you do is you'd plug in the 0, but when you do that, you get a 0. Then you always subtract the lower limit, so minus. Now what happens when you plug a -1 in? You just get 3 over 2 times 1. So I have 0 upper limit minus 3 over 2 for the lower limit, plus my second one, the upper limit would be 1 over 2, the lower limit just 0. So I get -3 over 2 plus 1/2 for a total answer there of -1. Now, when I think about that problem graphically, of course, my answer should match, and it does. It would be 2x minus the absolute value of x. What I did here is I just plotted some points. I said, well, what happens if I plug in a -1? If I plug a -1 into that expression, I would get -2 minus the absolute value of -1. Well, that's -2 minus 1. That gives me a -3. have the ordered pair -1, -3. When x is 0, 2x minus the absolute value of 0 is still 0, so I get the ordered pair 0, 0. And then for my other point, I just plugged a 1 into that expression. 2 times 1 minus the absolute value of 1, that's just 2 minus 1. When x is 1, my y value is 1. So then I drew out the line that gives me the region from -1 to 0. I drew out the line that gives me the region between 0 and 1. This one had a slope of 3. This one had a slope of 1, just like I knew it would have. Now, in that first region, you can see, and you'll see it, I put for the overall area A, I broke it into region A1 and region A2. They're both triangles, so 1/2 base times height. 1/2, the base here is 1. The height goes from 0 to -3, so it's -3. 1/2 base times height, 1/2 1 times -3. My other one, 1/2 base of 1, height of 1, gives me the 1/2 there. -3/2 plus 1/2, same answer, -1. And again, that answer of -1 just tells you that there's 1 square unit of area more beneath the x-axis than there is above the x-axis. And you can see, looking at my 2 triangles there, clearly the triangle beneath the x-axis has greater area than the triangle above the x-axis. That's why the overall area was negative. Now, moving to a problem which I think summarizes what we're doing pretty nicely. For this one, I'm wanting us to find the integral from 2 to 5 of 2x plus 1 with respect to x 3 ways. The first way, using an infinite Riemann sum. The second way, using geometry. The third way, using integration. So my favorite way, the infinite Riemann sum way, you say, well, okay, that's going to go back to the R sub n formula that says it's the summation from 1 to n as n approaches infinity of f of a, where a is just your first part in this problem. In this problem, it's starting at 2, so a is going to be 2, plus I times delta x. Delta x is the width of each rectangle. The width of each rectangle is always the end point minus the beginning point, 5 minus 2, which is 3, divided by the number of intervals, which is n. So delta x is going to be 3 over n in this problem. Of course, times delta x, 3 over n here. That's what I've done here. F of a, which is 2, plus I times delta x becomes 3i over n. And of course, times the delta x, 3 over n on the outside. I brought the 3 over n on the outside, or sorry, times the summation on the outside. And then I took the functional value here. F of 2 plus 3i over n becomes 2 times the group 2 plus 3i over n plus 1. All that is plugging it into your function in your problem. And then algebra just says, well, I'm going to have 2 times 2 plus 1. It gives me the 5. I'll have 2 times 3i over n for 6i over n. So this problem simplified really nicely. I know that the summation of 5s is just 5n, so I broke the sum down into 2 separate terms. The first term is just going to be 3 over n times 5n, since the summation of 5s is 5n. And then the second one, I'll have 3 over n times 6 over n times the summation of i's. By formula, we know that the summation of i's from I equals 1 to n is going to be n times n plus 1 over 2. So I plug that in the next step, along with saying 3 over n times 6 over n gives me 18 over n squared. I went ahead and also canceled out the n's in the first one and just said 3 times 5 is 15. Now, for this second one, I know that the leading term in the numerator will be 18. It'll be multiplying the n squared. No other term is important because it's infinitely times smaller. In my denominator, I'll have a 2n squared. Well, we know the limit as n approaches infinity of 18n squared over 2n squared is just going to be 9. So we have our 15 plus 9 for our final answer of 24. Now, when I try to match that gorgeous answer we get by using the Riemann sum with geometry, geometry kind of pales in comparison. It's so much easier. You say, just plot out your line. And all I did is I plotted 2 points on it. If you plug in a 2, we know 2 times 2 plus 1 is 5. We have the ordered pair 2, 5. Plug in a 5. 2 times 5 is 10 plus 1 is 11. We have the ordered pair 5, 11. Any line is determined by those 2 points, so I just connected my line. Now we needed the area underneath that line. So I split my region up into 2 easy figures, a rectangle and a triangle. I know that the rectangle has a base of 3 and a height of 5. So that's where this 3 times 5 came from. The area that I have labeled A1 is the triangle. We know it's going to be 1/2 the base, which is again 1/2 times 3. And the height goes from 5 to 11 for 6. So I have 1/2 times 18 is 9 plus 15. I get my 24 again. Please notice the numbers matched out to be the same. 15 plus 9, 15 plus 9. Gorgeous. Now, for my integral, whenever I do the integral, it's just the power rule. So you'd say, well, okay, if you're integrating from 2 to 5 of 2x plus 1 with respect to x. And whenever you integrate, you really should have a parenthesis around the term in there because this is a product in there. It's 2x plus 1 times dx. If you don't put the parenthesis in there, it looks like only the 1 is multiplying the dx. Do some people have sloppy notation quite often? Yeah, and a lot of people overlook it. But if you're really wanting to be accurate with your notation, that parenthesis needs to be in there because it's f of x times dx. All of that function is multiplying. Now, I'll always try to be accurate with my notation. Now, notice in the next problem, no parentheses because that's all one term. No need for a parenthesis there. Needed here because it was a binomial. But now, back to the problem. If I integrate 2x, well, 2x to the first becomes 2x to the second over 2. The 2's cancel out and you just get x to the second. This is understood to be 1x to the 0. When you integrate it, it becomes 1x to the first over 1. So you just say, well, it's just x to the first. Now you're evaluating that integral from 2 to 5. Now it's correct when you evaluate an integral, you can use the bracket notation like I'm using here, or earlier you might have noticed I just used a vertical bar in the evaluation. That's also correct. Both are, I did it right here in this problem, both are accurate ways to evaluate an integral. This is an evaluation bar versus an evaluation bracket. Usually when I have multiple terms, I use the bracket. If I just have an individual term like here, I'll just use the bar. It doesn't really matter though. I just think this is a little neater. Now, when I evaluate this, I plug the 5 in, I'll get 25 plus 5, that's that one, minus the lower limit, which is going to give me 2 squared plus 2. I'll get 30 minus 6, 30 minus 6, 24. Clearly our answer matches no matter which method we do, which obviously should be the case. The next one, we already saw a problem similar to this with my cosine where I had the areas canceled out in it, but that cosine was going from 0 to pi where the areas canceled out. Notice if I look at the inverse tangent function, you're supposed to remember, well, the tangent graph looks like y equals x cubed, but it's stretched between 2 vertical asymptotes going from negative infinity to infinity at negative pi over 2 to pi over 2. Well, the graph of the inverse tangent function, always remember, looks more like the cube root of x, but it's going to have horizontal asymptotes, one at pi over 2 and one at negative pi over 2. Now, we're just starting this from -1 and going to 1. So when I thought about, well, the inverse tangent of -1, well, the angle on your unit circle in which the inverse, on which the tangent is -1 is at negative pi over 4. So I can say, well, I know that the inverse tangent of -1 is going to be negative pi over 4. So I'll plot that for my y value there. And then the inverse tangent of 1, that's asking you, when is the tangent function 1? Well, that's at your angle of positive pi over 4. So we're just going from -1, negative pi over 4 to +1, positive pi over 4. Now, if you have a really good trig background, that graph doesn't give you any distress at all. If your trig background's kind of weak, you're like, ooh, I'm not sure where you got that. It's not a huge deal. But the huge deal is that you just do see that, well, obviously now, once you've seen it drawn out, this negative region would cancel out with this positive region. So I would say, well, then what's the answer for the integral from -1 to 1 of this? The answer is 0 because the two areas are equal and opposite. Now, instead of just limiting us to think about that inverse tangent function in here, what I would like you to be thinking about is that if this were any odd function, it could be a cube root, a fifth root, any odd root, or any odd power, like an x cubed, an x to the fifth, an x to the seventh. Clearly, an inverse tangent is an odd function. If you have any odd function, remember, odd functions are symmetric with respect to the origin. Anytime you have a function that's symmetric with respect to the origin, if you try to evaluate it from -a to a, where a is any value, it could be -10 to 10, -20 to 20, -1 to 1, as in this case, -pi to pi. Anytime the beginning and ending are the same, are equidistant from the origin, you know your answer is 0 because your areas are going to be equal and opposite, thus cancel out. Up next. This one, just a simple power rule here. I wanted to throw in another variable just so that you see it's not always x. It can be any variable you want in there. But whatever variable it is, your integration has to be with respect to that variable. Now, technically, what I'm asking you to do here in this problem is to find the area between the curve 6y squared plus 7y plus 1 and the y-axis from y equals 0 to 3. You don't really have to worry about that because the integration power rule takes care of all of that for you, though. So you just say, okay, if I integrate the first term, it becomes 6y to the third over 3, gives me 2y cubed. Second term, 7y to the second over 2, get that. That one I need to think of, that's the same thing as 1y to the 0. So when I integrate it, it becomes 1y to the first, that right there. We evaluate this from 0 to 3. I know when I evaluate all this at 0, it's not going to amount to anything. So you'll notice I didn't even worry about that over here. When you subtract the lower limit, it's just going to be -0. So the only thing we have to worry about is the upper limit. You'll have 2 times 3 cubed minus 7 over 2 times 3 squared plus 3. This gave me 2 times 27 is 54. 63 over 2, 7 times 9 is 63 over 2, and then plus 3. Added those together. Whether you get an answer of 177 over 2 or 88.5, oftentimes achieve will want a fractional answer. That's the reason I put the 177 over 2 there. Of course, both answers are fine for me. Now, the next one, again, power rule. If I ask you to integrate from 2 to 0, please don't always think that your lower limit has to be less than your upper limit. It's not the case. So for here, I'm integrating from 2 to 0. Now, if you wanted to flip those around, you could. If you change the sign out in front, you could say, well, this is equal to the negative of the integral from 0 to 2. No reason to have to do that unless you just wanted to. You could. I left it as it was, and I just said, okay, the first one, the integral of x squared is x to the third over 3, or you could have said 1/3 x cubed, of course. Now remember, exponential functions, derivative of any exponential function is that exponential function. Same thing when you integrate. The integral of any exponential function is that exponential function. So the integral of e to the x is e to the x. Now we need to evaluate from 2 up to 0. So your upper limit is 0. We evaluate at 0. When you evaluate at 0, the first term is 0, but the second term is not. You have to remember any number to the 0 power is 1. So that upper limit, I'm going to get a -1 there. The negative e to the 0 is -1. Now you subtract the lower limit. When you plug in the lower limit, 2 cubed is 8. You'll have minus the group 8 over 3 minus e squared. But now, since you're subtracting that lower limit, you can see that that e squared is going to become positive. You'll have a -1 minus 8/3. That's -3 over 3 minus 8 over 3 is -11 over 3. If you needed an exact answer, -11 over 3 plus e cubed would be fantastic. Sorry, I said e cubed. E squared would be fantastic. That's also approximately equal to, and I've rounded to 3 decimal places, 3.722. Now, easy question. If you get it, let me make sure you get it, though. If I ask you to express as a single integral the integral from 7 to 3 of f of x dx plus the integral from 3 to 9 of f of x dx. What I'm wanting you to remember here, guys, is that this is telling you, hey, I have all of the area from 3 to 9 of f of x dx. What is this one doing? Well, it has the reverse limits, which means it's the same thing as minus the area from 3 to 7 of f of x dx. So you say, well, if I have the area from 3 to 9 and I'm subtracting the area from 3 to 7, then I still have the area left from 7 to 9. So I want you to see that this is equivalent to the integral from 7 to 9 of f of x dx, because that first one is subtracting off all of the region from 3 to 7 out of this region from 3 to 9, leaving us what's left over from 7 to 9 of f of x dx. Last problem I want to look at with you. Sometimes we're not able to integrate it all. In fact, we will not be able to integrate this function all semester long. That's a pretty complicated integral. If I ask you to integrate from 0 to 1 of 1 over the square root of x cubed plus 4 with respect to x, and I say, well, okay, let's say we can't integrate it. Then I need to find a way to approximate what the solution would be without integration. So here's where you think about it. And what you should automatically know is all fractional functions like this that have a denominator that's going to get greater as x gets greater, you know it's going to be a decreasing function because you're taking the same numerator, dividing it by a larger and larger denominator. It's going to be decreasing. So I said the function is going to be decreasing, and it's obviously decreasing on 0, 1. It's technically always decreasing, but we'll say it's decreasing on 0 to 1. That's the only relevance here. Now, I went ahead and plugged in the 0, and you get 1 over the square root of 4, which is 1/2. We know we'd have the point 0, 1/2. Now my curve is going to be coming down through here. What's the ending point? Well, the ending point is at x equals 1. And you said, well, if you plugged in a 1 here, you'd have 1 over the square root of 1 plus 4. It's the square root of 5. So 1 over the root of 5 is my second term in there. My first term had a height of 1/2. So I can see, yep, my curve did decrease in that region. I need to try to estimate what the area under that curve is. That's what my integral would be. So the integral would be the exact value of the area under that curve. Well, what I can do if I'm just wanting to determine an upper and lower bounds, since it's a decreasing function, if I use a left-hand rectangle to estimate it, I know it's an overestimate. So if I used a left-hand rectangle, you'd say, well, its height is going to be 1/2, its base is going to be 1. So I can absolutely guarantee you that this integral is less than or equal to base times height, 1 times 1/2. It's less than or equal to 1/2. That's the left-hand estimate. Well, what about the right-hand estimate with one rectangle? And one rectangle will be fine here. Well, the right-hand estimate with one rectangle, the height would be 1/5. The base is again 1. So you'd say, I know that the area under the curve is well, in fact, it is strictly greater than. It's okay to say greater than or equal to 1 times 1 over the root of 5. And that's going to give me the 0.447 as a decimal there. I just wanted to go ahead and get the decimal for that. Now, if you wanted to here, and you can see where I got the 0.447 there. If you wanted to, what you could do, if you wanted to see this out, I'll go ahead and graph this problem. This problem was 1 divided by the square root of x raised to the 3rd plus 4. Now, we know our values are pretty small in here. What I think I'll go ahead and do here, try to make that more clear. Yeah. What I think I'll go ahead and do here, I'll go to my window. I'll go negative 0.5 to 1.5, zoom 0. Oh, my function doesn't decrease much at all. That's okay. So I'm interested in what this looks like from 0 to 1. And I want to try to find the area under the curve there. Now, I don't have as good of a graph as I would have liked, but that's okay. I'll go ahead and go second calculate. I want to calculate an integral. It's second calc 7. This integral is going to start with a lower limit at 0, and it's going to go all the way until x is 1. I'll hit enter. It'll shade in the curve I'm looking for, and it will tell me what the answer is. So the area, and now this is not an exact answer, it's still a decimal approximation, but the area under the curve is approximately 0.485839, which, keep in mind, that's just about right in between these two. We knew it had to be less than 0.5. We knew it had to be greater than 0.447. Well, it is between those two values. It's 0.4858. So this would give you a really good lower and upper bound. Okay, this should pretty much prepare you for the problems in section 5.2. Hope this made sense. Please let me know if you have any questions. I'll always be glad to help.